All right, test, perfect. Awesome. All right, hey everybody, happy Monday. I hope you guys are doing good. If you're not in Ames, the weather was pretty good today, actually. Got some sun. It looks like it's about to rain now, but the day was pretty good. It's April 20th. We're only like 10 days away from May 1st, which is crazy. Semester is drawing down, and hopefully it's not getting too busy for you guys. God knows that it just gets busier every day. But we've hit some cool stuff. We're going to talk today about some surface integrals and flux. And that's all we'll talk about. We'll basically do a few different surface integral problems. There aren't too many of these, especially scanning old exams. But it definitely doesn't mean you wouldn't be asked about them, especially if it's an online exam. So we'll do some surface integral problems. It's pretty much just using an equation and hoping stuff works out. And we'll also have some flux problems. Nathan asks, how do I feel about the semester ending? I don't know, because I got to go into the real world in a couple months here, so that'll be interesting. We'll see. I don't know. I'm excited to take the summer off, though. All this means I definitely got to take the summer off. So yeah, I know I got to start adulting. Oh man. Hey, Caleb, and Caleb just joined. But yeah, so yeah, I don't know how I feel. It's gonna end, and that's how it's gonna be. So we'll see. But Calc 3 is here to keep me busy and keep me distracted from thinking about those things. So I think that helps. But thinking about Calc 3. All right, let's look at it. So you guys saw this equation, and we'll write it down before we use it. R of. So well, I guess we can start with. We talked about G. That just means a surface. For some reason, we use the letter G. G of X, Y, and Z, and then it's like a D of the surface area. Or D sigma is usually used. If you go on like Wikipedia or something, they'll use D sigma, or maybe some other textbooks. But this will convert to a radius, and we use G of X, Y, and Z, and then we have the square root of partial X squared plus partial Y squared plus 1. Ooh, remember, reminds us of our kind of tangent plane equations, dA. So, and the tricky thing about these problems is this Z is actually just going to be Z is equal to a function of F and Y. So you have to make sure you plug that function into your Z. And we did that in lecture. But yeah, so not too crazy. When you do these problems, really you just have to find Fx, Fy, and plug in your Z, and then basically run it down. You might have to convert it to polar. You might not have to. I think one we're going to do is convert it to polar. But we saw this in lecture. So I'm going to set up the integral for the following problem. So we have let G be on the surface of f of xy is equal to 1/3 x squared x cubed plus 1/2 xy over the region 0 is less than or equal to x, which is less than or equal to 1, and 0 is less than or equal to y, which is less than or equal to 2. And then basically find this surface integral, and they give you the surface integral equation. So if we look at it, so remember we need a couple of things right off the bat. We need an f of x. F of x is equal to, oh, easy, x squared. F of y is equal to, so it'd just be y, perfect. Z is equal to just this, so I won't necessarily write that, but we know that's there. And now we plug everything in, so we'll have the integral. We're going to the region now. So we have 24 times Z. So Z we have to plug in basically our surface. So our Z is going to be 1/3 x cubed plus 1/2 y squared. And after we plug in our surface, then we have times y, just a y, minus 12y cubed. And this whole thing is then multiplied against the square root of x squared, partial f, or partial x, plus partial y, squared plus 1, and then we have dA. Okay, so now once we figure that, the question just says set it up, so we set it up. We can simplify it if we want to, but this is how you would set up one of the problems. And you can see that you could probably solve that integral now, and I think this was an exam question or a practice exam question. And it gets a little nasty, but we won't solve this one. But just so you guys kind of see what goes on there. Let's see if we can Oh, there should be a second problem, but I guess we don't have it, which kind of stinks. Oh well. You have been hired to help design one of these rides. So we've seen this problem in lecture. Actually, wait, just kidding. Let me see if... Oh, no, it's not there. Dang, I don't know what happened to the third problem I have. All right, but we'll look at this. You've recently been hired to help design rides in an amusement park. One of these rides that you're working on involves a large bowl-like surface. In particular, the surface is that for 0 is less than or equal to z, which is less than or equal to 2. And then you get your density. Don't write this whole problem down in your notes. All I want you to write down is just write down the z, write down the bounds, and write down the density. Don't worry about all the words. You can find this online. And I believe this was in a Butler. It wasn't the same numbers, but it was in a Butler's lecture. So we have z is equal to 1/2 x squared plus y squared. The second one was 0 was less than or equal to z, which was less than or equal to 2. And we have our delta function, z. And God, we hate word problems, and I almost just didn't. This is probably one of the first big word problems that you've seen me do, because I don't like the word problems either. But it was on an exam, and it was in a lecture, so I think this one's kind of important, I guess. And I guess if we don't like to do it, that's even more reason to do it, so we can get some practice. So we need to find the mass, the total mass. And remember, this is kind of a cool problem because we kind of bring it back. Mass, if you just integrate over the region, the density, then you've got it right there, which is really cool. So what happens is, because it's a bowl-shaped surface, so it's kind of, you might see a bowl-like surface, you might see hollow surface. If you see hollow surface or hollow cylinder or something like that, that definitely means we're going to use surface integrals and not regular integrals. But so we use not dA, but we would say G dSA. And that density will give us the density of that surface, and we can find the mass from that. So now we would set up our equation, right? M is equal to the region. And we would have to basically do everything where we have g, x, y, z. And then we'd have the square root f of x plus f of y plus 1. Oh, and these are squared. And then it'd be a dA. So I'm going to let you guys run with this problem, see how far you can get down it. Remember, it's find your f of x, find your f of y, square them, plug them in, simplify your equation a little bit if you can, and we'll see how you guys go from there. I might draw out this surface. If you don't hear me saying anything, I'll be drawing it out in silence so I don't distract you guys. But that might give you a hint for setting up your bounds and maybe solving your final integral. So if I'm drawing stuff and I'm not talking, don't worry. I know I'm not muted, but yeah. All right. I'll let you guys go for it. I'll set a timer on my end for like 3.5 minutes, and we'll see how you guys do. Good luck. I believe in you. Alright, so you've seen I've drawn that plot there of our z is equal to 1/2 x squared plus y squared. Remember that our z goes from 0 to 2. So if our z goes from 0 to 2, whatever z is equal to 2 right there, we'll get our radius. So you could say z is equal to like 1/2 r squared if we convert that to polar, that x squared plus y squared. So if we convert that to polar, and at z is equal to 2, r is equal to 2. So this radius right here would be 2 when you're solving for your bounds. I'll let you guys go for another couple minutes. I bet you're working hard at it. I bet you're doing a great job. So yeah, I'll set a couple more minute timer. All right, but let's bring it back together and see how far you guys got, how well you did. So we've got, we solved for f of x. Remember, we're solving from right here. Oh, I should not be using black. Hang on, let's use blue. There we go. So we're solving for f of x. It's pretty simple. We'll get our f of x is equal to, so we could distribute this out to, it'd be like 1/2 x squared plus 1/2 y squared. To take the derivative of it easier. So then we get f of x is equal to x, f of y is equal to y. Okay, perfect. And then if we plug everything in, m is equal to, maybe we'll do that in a different color. M is equal to, so we have a region, and our g, x, y, z, we're pulling as just our density function. So it's just z. And then the square root of, so we've got f of x, which is x squared, plus y squared, plus 1, and then we got dA. Remember that we have to substitute out our z, which becomes, and maybe I'll just do that here to save space because I think we're going to run low on space. Our z becomes 1/2 times x squared plus y squared. Okay, so you can see there's a reason I gave you a radius because we're definitely going to want to switch into polar coordinates. So I say we just make that switch right now. We have a region. I'll bring the 1/2 out in front. So we've got r squared times the square root of r squared plus 1. And then the dA, remember, has to go to r dr d theta. So we'll have an r cubed out in front there. And then if we do that, we'll have to set our bounds now. So if we set our bounds, remember that. So I kind of drew this picture. When we talk about the dA, we're talking about that flat area that function exists on top of in the xy plane. So that's our like dA. So our dA, our area exists. It's full revolution, so it's 360 degrees, which is easy, 0 to 2 pi. Perfect. And our radius, it goes from 0 to 2, kind of like how I showed you guys before. Usually finding that radius is the trickiest in these problems right here. So we found a radius is 0 from 2, and now we just have to basically solve this integral. So we got 1/2 0 to 2 pi, 0 to 2. So we'd have r cubed square root of r squared plus 1 dr d theta. We could do the little Butler trick where he pulls out the d theta because we don't really care about it, and the 1/2 really if we want to. So it'd be like 1/2 be 0 to 2 pi d theta times, then we'd have 0 to 2 r cubed times the square root of r squared plus 1 dr. Okay, so now we have that. I'll let it, there's the dr. All right, cool. So we have that. Now we just need to solve it. This guy on the left just becomes 1/2 times 2 pi, which is in just pi. The guy on the right will probably have to do some sort of trick to solve this integral. If you think about what it might be. Yep, if you thought u substitution, you were right. So we'd have to do a u substitution, and our u is probably going to be whatever's inside that integral. Or not integral, excuse me, square root. So it'd be r squared plus 1. So our du would become 2r dr. We don't have a 2r, but we do have an r cubed. And if you've seen this, I remember I did this a lot in Calc 1. I think my high school calc teacher made me do it just over and over a lot. But we have that dr becomes easy, so we'd have a du over 2 is equal to r dr. So that'll take care of one of the r's in the dr. And then this guy, if we move the r squared to the other side, we get r squared is equal to u minus 1. Excuse me, 1 minus u. And if we do that, then we can plug in 1 minus u for the rest of that r squared. So if my computer screen will move, we can have 0 to 2 of, so we'll have the 1r and the dr goes away to a du over 2. And then the other r squared becomes 1 minus u. And then the square root of that's actually our u. A little tricky u substitution problem. And once we do that, now we just solve that integral. And you say, how do we solve it? Now we still have two terms. Well, I'd say just bring out 1 minus u, and then times u to the 3/2, or not 3/2, sorry. 3/2 is coming, u to the 1/2, du over 2. And then that becomes 0 to 2 of 0 to 2 of u to the 1/2 minus u to the 3/2 du, and I'll put the 1/2 in front. And I actually made a mistake. It is u minus 1. Well, if we have the r squared, we would have to bring, so u is equal to r plus 1. The u would have to be subtract. Oh, you're right. Yeah, it is u minus 1. Thank you, Nathan, for catching that. So u minus 1. Excellent catch. So it'd be u to the 3/2 minus u to the 1/2. And I actually made another mistake. Does anyone see what I made? One more mistake. See if anyone in the chat can catch it. That I should have done. Lost pi. Yeah, I did lose the pi. The pi I'm bringing down. I was banking on that. I had it in the bank. There's one more thing. Anybody? Nobody. I forgot to switch my bounds. I didn't switch my bounds. My bounds are still 0 to 2 even though I did the u substitution. My bounds should be, if I plug in 0 to u, it should be u is equal to 1, and then 2 squared plus 1, u is equal to 5. Yeah. So we got 1 to 5. Yep, so my bad. Man, that would not have been fun to do that out. Okay, so then we'll get 1 to 5, 1 to 5. Cool. Making all sorts of progress by learning. All right, cool. So now we've got u to the 3/2. Okay, now we have to integrate that. So it gets a little messy. It'll be 1/2 times. So then we get so 1 over 3/2 plus 1. So 3/2 plus 1 would become 5/2. So it'd be 2/5 u to the 5/2 minus, and then it'd be 2/3 u to the 3/2, and we integrate that from 1 to 5. Okay, now if we're on the exam, what I would do is plug everything in and box it. And this is an exam problem, and actually the solution that they have for the exam. Man, it didn't even. I usually post something must have got lost in the transfer to PDF. I must not exported the right version. But in the solution for the exam problem, it's also they just plug it in and box it. So we'll have pi times this big thing. So we've got 2/5 u to the 5/2, but it's not u. Sorry, it's 5 times 5 to the 5/2 minus 2/3 times 5 to the 3/2. And then it's that whole thing minus, so then actually it's minus, and then we've got 2/5 times 1 minus 2/3 times 1, and that whole thing is, and then you would just box this as your final answer. Definitely not want to solve that. 1/2 got lost. Yes, it did. Yeah, so it'd be pi over 2. Excellent catch. Nathan's on top of it today. All right, cool. Are there any other questions about that? I mean, that's as tricky as a surface integral problem will be, and I guess it was pretty tricky, and it involved a few different things. But this is probably one of the only exam surface problems I've seen. What we mostly use surface integrals for is flux. And if anyone's taken Physics 222 yet, you've done a lot with flux. And God, it doesn't end. Green's theorem and, or not Green's theorem, Stokes' theorem and Gauss's law, I think. There's a lot of flux going on. But so when we talk about flux, we're talking about stuff that goes in and out of a surface. So you might have seen like the F dot N d of SA, and there was a whole derivation on that. And what we use is negative m f of x minus n f of y plus p dA. Really easy. Really easy. And the fact that you guys, so lucky you don't even have to memorize all these equations. Imagine all these equations you have to memorize, divergence and curl and flux and Green's theorem and soon Stokes' theorem and all this crap. Nope, you can all have it on a note card and take the exam. So that's kind of nice. So we've got this guy right here. Write it down. Keep it nice and organized. Don't lose the minus signs. And you'll get through this pretty well. So let's look at this. Review this from your notes or try by yourself. This question from lecture. If you need the notes to help you get through, if you took notes from one of Butler's lectures, you've seen this before. If not, see if you can try and find it yourself. And we'll see how you guys do. I guess I'll write the equation again so you have it. Minus f of x minus n f of y plus p dA r. And remember that this would be your m, n, and p. And then you would have to find your f, x, and fy from that equation. So I'll set a timer for a few minutes here, and I'll let you guys run on it, and good luck. I believe in you. All right, if you're working on this and you can't figure out your bounds, I'm going to tell you that your bounds are from 0 to 2 pi for your theta, and for your r, they're going to be from 0 to 1. I don't think you'd ever be expected to derive that on an exam, but you never know, I guess. But yeah. All right, let's see how you guys did on this this flux problem. All right, so you can see I gave you that little hint from the lecture. We derived that. I don't know if we'd ever be expected to figure that out in the exam, but you can figure it out if you would like. But if we look at it, plugging just basically, well, I guess we could start with finding f of x before we do this. So fx is equal to negative 2x, nice and easy. Fy is equal to negative 2y. Okay, good to know. And now we've plugged that in. I'll do that in a darker color. So we have a region, negative m. So m is x, so it'll be negative x times our f of x, which is negative 2x, minus our n, which is y, times our f of y, which is negative 2y. And then we get plus our p, which is z. Remember that z is going to be 1 minus x squared minus y squared, so we'll just plug that in instead. And we've got our area. So now we can simplify this a little bit. We have a region, it'll be negative 2x squared minus, positive 2x squared, and then plus 2y squared, those negatives add up, plus 1 minus x squared minus y squared dA, and then we'll just get the region on its x squared plus y squared plus 1 dA. Sweet. And of course we can push that forward into polar coordinates, so it'd be r squared plus 1 d. Well, it'd be r squared plus 1, and then we need the dr d theta, right? So then it'd be r times dr d theta. And we go from 0 to 1 and 0 to 2 pi. And that's pretty simple integral we solve now. You could bring out the theta 0 to 2 pi, the d theta in front, that's just 2 pi, times, then you got 0 to 1 of r cubed plus r dr, and then there's no d theta. If you solve this guy out with it, you've seen it in lecture, you can solve it pretty quick too. You'll get 3 pi over 2. But yeah, that's a pretty simple flux problem. Finding the bounds was probably the hardest part. But yeah, and are there any questions about the general procedure of flux problems? Awesome, the silence is great. All right, cool. Well, let's move on and try maybe computer's being weird. Try another problem. This is from Spring 19, problem 6. Find the flux through the surface using upward normals defined by f of x is equal to, basically right there. And it's a little tricky because what happens is they give you your m, n, and p as just vector components. So they don't say big F is equal to. But because you see the vector field, remember big F is just a vector field, you have your m, n, and p right here. So don't get tripped up by the notation. That's probably the trickiest part. And you can see the region if we graph it really fast. Let's all do that together before we start. Just think about what that might look like. Think about it. Sketch it on your paper. Yeah, and if you drew big old donut, then you would be right. Because x squared plus y squared is just a circle, and this is x and y, of course. So this is the r is equal to 1, and then r is equal to 2. So 2 and 1. So yeah. All right. I will let you guys get going on that. I'll set a timer for 4 more minutes, and we'll see how you guys do. Good luck. All right, so it is 5:47, so we're gonna get pushing on this problem. But let's look at it. So I kind of sprinkled in some hits. You got your f of x and your f of y. So if we write the whole thing out, we will get, and I'll do it. Let's do it in light blue. So we do the whole thing out. We'll get the region. Negative m is x, negative x times 3x divided by the square root of 3x squared plus 3y squared. And then minus, we've got y times 3y over square root of 3x squared plus 3y squared. Okay, and then we need our p, which is just xy squared plus xy squared, dA. So we've got our dA there. So let's push on. Basically, you can see that we're probably going to combine like terms with this, or not combine like terms, but combine those terms because they have a common denominator. So if we do that, we'll get r, that negative 3x squared minus 3y squared. And then we've got the denominator, square root of 3x squared plus 3y squared, plus xy squared dA. So we want to convert this to polar because I think that's going to be the easiest way to solve it, especially because our region is really well defined in polar. So to do that, you see we've got some xy squareds, or x squareds and y squareds, but we have some pesky 3's in front of it. So what I would do is pull out the 3's in both the numerator and the denominator. So we get the region of, so it'd be negative 3 over the square root of 3 times, then what we would get is x squared plus y squared over the square root of x squared plus y squared plus xy squared dA. And now if we do that, it's pretty simple math, and I guess I could prove it really fast. If you have like a over a to the 1/2, what happens is that's just a to the 1 times 1 over a to the 1/2, or a to the 1 times a to the 1/2, negative 1/2. So that it's really like a 1 minus 1/2, so it's a to the 1/2. So all I'm trying to say here is that this negative 3 over square root of 3 is equal to the square root of 3. And then that this x squared plus y squared over the square root of x squared plus y squared is equal to the square root of x squared plus y squared. You've probably seen it in reverse if you had a high school teacher that said, no, you can't have radicals in the denominator, or if you had to do that in Calc 1. It's the same thing, just in reverse. And then we'd have plus xy squared dA. Okay, so that was kind of the big trick out of this problem that I really wanted to point across, because now this turns into a really easy polar problem. It's just our radius, so we have the square root of 3, I guess negative, sorry, I lost the negative sign. And then the square root of x squared plus y squared, so it'd be r, and then plus, and this is the other thing I wanted to cross. So we have, I'm surprised we haven't seen this before, because I've seen this in Calc 3 when I took it all the time. The integral of xy squared dA, and if we look at it, and it's like an even or odd function. If we look at it where the same amount of it is on either side of the x-axis and the y-axis, this is equal to 0. And because of that, you could say that it's just symmetric across the y-axis. So you know, if you plug in a point at like negative 1 and 2 and 1 and 2, they would both become, so you know, you plug in negative 1 and 2 and it'd be negative 4. And you plug a point in at 1 and 2 and it'd be 4, so you get 0. It's kind of like an even function, but just with terms. Definitely kind of something just to put in the back of your head or put in the feather of your cap. It's kind of easy to see. So we can pull that across, and you know how you can split integrals up when you have an addition sign in the middle of it. So we could say 3r dA plus this guy xy dA, and then this guy just goes to 0. That's pretty nice. I don't know if you've seen that in your homework problems yet or not, or maybe you've actually done the math out for it, but yeah. And then after we solve that, then it's just a pretty simple integral. The bounds, as we can see, are from, so we'd have to do negative, so we've got the square root of 3r, then it'd have to be times r dr d theta, And then our bounds. All right, everyone say it out loud in your head, just to yourself. Your dog's going to be kind of weirded out. The theta bound is from, 0 to 2 pi. And your r bound is from, 1 to 2. So 1 to 2. Awesome. So now we have our bounds, and we can just solve that integral. And it actually gets a little nasty, but if you solve it out, you'll get 2 pi, because we still have that 2 pi from the d theta, and then we get the minus the square root of 3 over 3, and then it'd be 8 minus 1, I guess it would be 7. And again, I just boxed the answer when I found it. But it's 5:53. I want to get to one last problem before time is flying. This guy is also a fun one, but we're not going to do it. Everything cancels. It's a really cool problem because you do this integral, and when you combine the m and the fx and fy, everything cancels. It's really cool. But I guess we're not going to do it today. I do want to get to the quiz problem. We do have one quiz problem. And I finally get to use the meme. We've trained for this. It's our moment. So let G be the part of the surface lying above R, which consists of 0, blah, 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 flying the flux. For this guy, through G, where n is the upward pointing normal, it's 5:53. I'll let you guys try and do this until 5:57, and then we'll come back together. I believe in you guys. This arctan, remember we have an arctan of z squared in there. I really hope that arctan cancels out. I think it will. Your mfx and your nfy might cancel out. Might be a really easy problem. We'll see. All right. Good luck. I'll be back at 5:57. All right, let's see how you guys did. So we find our f of x. You would have gotten 3x minus 3x squared. F of y turns into 2y. So if we plug all that into our equation, we'll have a region. M is 2y arctan of z squared. And we multiply that by negative 3x squared. And then we'll get minus, and I guess there should be a minus sign in front of that, shouldn't there? Minus we get 3x squared arctangent of z squared times our f of y, which is 2y, plus our p, which is z, but it's not z. Z is equal to y squared minus x cubed, so y squared minus x cubed dA. Okay, so if we look at this, we've got a 2y and a 2y, and then we've got a arctan z squared, and we've got a 3x squared and a 3x squared. Their signs are different because it becomes a positive over here, doesn't it? So if it becomes a positive, one's a negative, they cancel out, which is perfect. Because we get rid of that arctan and we don't have to integrate any of that garbage. So we've got r, so we'll have y squared minus x cubed dA. Oh, and we can definitely do that. All we really need to know is the region. God, I hope it's not polar because that'd be hard to get to polar. Oh yeah, look at, they gave us the Cartesian coordinates. Perfect. So we got 0 to 1 and 0 to 1. Oh, even easier. So we can write 0 to 1, 0 to 1, y squared minus x cubed, and we can just choose dx dy or dy dx. We'll do dx dy. And if we do that, we get 0 to 1. So integrate with respect to x first, so we'll get x y squared minus 1/4 x to the 4th, evaluated from 0 to 1. And if we do that, we'll get y squared minus 1/4 0 to 1 dy. And then if we do that, then we'll get 1/3 y cubed minus 1/4 y from 0 to 1. So we'll get 1/3 minus 1/4. Boom. Awesome. All right. Well, it's 5:59, and that's all I've got. If you guys have any questions, feel free to shoot them. I'll stick around here for a second. Otherwise, our next session is Wednesday at 5:10. I think I'll bring like a Kahoot or something. We'll do something kind of fun at the start. I feel like we kind of need to liven up and keep our sanity in the quarantine. But until then, you guys stay safe, and I'll see you later.